Section 7.3 is about equations that are quadratic in form, and really what that comes down to is it goes back to in section 4.5 when we had to factor by substitution. That's a thing that comes back right here, essentially. So that's why on this first page, it's basically just a couple of examples of that, because that's the thing that you have to be able to do to solve these equations. So going back to section 4.5, when you have something like this, where I copied that verbatim from 4.5, where the thing that's that filled in square, it's some expression. Or maybe that's x raised to a power other than 1, like a number 1 where we have the x to the fourth and the x squared. So what you end up with is you still have powers of x, where one of them, like one of those exponents is twice the other exponent, but they're not x squared and x or something else. So maybe an x squared and an x to the fourth, or maybe like an x cubed and x to the sixth or something like that. The other thing is maybe the thing that's being squared and then also appearing to the first power in the next term, maybe that's not just a variable. You know, maybe it's like x plus 3 or x squared plus 5 or something like that. Right? So it's something a little more complex with multiple terms, usually a binomial. I guess you could have something longer, but we're not going to. So let's see, if we're going to have to factor this thing, so this is just going back to section 4.5. If you look at what's going on here, you got the 2 powers of x in number 1, where one of them is twice the other. And I guess you could write it like this, maybe to make it look a little bit clearer as far as what's going on here. So I rewrote the x to the fourth as x squared squared because, well, I mean, that would work. You would get to the x to the fourth back because when you have a power raised to a power, you can multiply them together. But then you can see that the x squared is itself the thing that's being squared here. So for the substitution, what we're going to do is we would let u equal x squared, right? So then the substitution, in that step, what you would have is u squared minus 9u plus 20. And then that's going to factor. You need a pair of factors of 20 that add up to negative 9, which would be negative 5 and negative 4. So we should get u minus 5 times u minus 4. And then we want the answer in terms of x, not in terms of u. So we're going to have to back sub. And if we do that, we'll have x squared minus 5 times x squared minus 4. And if you're going to factor that, then this second part of the product, the x squared minus 4, that's a difference of squares. So we could actually factor that as x plus 2 and x minus 2. And then this right here, the x squared minus 5 times x plus 2 times x minus 2, that's the fully factored version. Then with number 2 is a similar idea, except that the thing that's being squared, and then which later also appears to the first power, it's not x to a power, it's a binomial, right? It's x plus 6. And looking at this, you go pretty clearly, that ought to be the thing that you're substituting for, right? Like that would be what simplified this a little if you subbed in for the x plus 6. So that's exactly what we're going to do. We're going to let u equal x plus 6. So then what we're going to have when we sub in will be 2u squared minus 11u minus 21. And then let's see, this does factor. So 2u and u. And we need a pair of factors of negative 21 that'll somehow give us that negative 11 in the middle. Let's see, I guess first of all, to get that negative 21 on the end, they'd have to be opposite signs. And to get the negative 11 in the middle, my first guess, which actually does end up being right, is to do this. Just because if I put the negative 7 down here, when we FOIL it, that would end up getting multiplied by the 2u. I figured that was the best shot at getting a middle term, or at least a coefficient that's that far away from 0. And that does work, because if you FOIL that back out, for the outer product, you'll get minus 14u, and the inner product's plus 3. So yeah, it looks like that works. And then we have to back sub. So we want the answer in terms of x, not in terms of u. So u is x plus 6, so we'll have 2 times x plus 6, and then plus 3 times x plus 6 minus 7. All right, so in this first big set of parentheses, you've got to distribute the 2. So we'll have 2x plus 12 plus 3. And then here, we don't even really need these parentheses to do the subtraction, right? X plus 6 minus 7, that's just going to be x minus 1. So that first set of parentheses, we're going to get 2x plus 15. And then in the second one, we're going to get x minus 1. And that would be the fully factored version. Okay, so that generally is the idea here. And what we're going to end up doing now is we're going to have to do this kind of maneuver just with an equation. So that's going to be the next step. All right, so let's see. We're going to solve an equation that's quadratic in form. And like you can see all those squares in there. So you go, yeah, okay. It looks like the same thing. And it's a similar concept, right? And even just looking at number 3, which is up on the screen right now, you can see it, right? You go, okay, yeah, there's an x to the 4th and an x squared. That kind of looks like the thing that we were just doing. Yeah, it does. There is a little bit of a wrinkle, which is that you can have imaginary answers. So that may lead to a whole bunch of answers. Like, for example, number 3 is going to have 4 answers, but we'll get there in a second. So what you want to do, just like with anything else, just like if you were going to use the quadratic formula, I suppose, you would want to get 0 on one side. Or if you were going to factor, right? If you were going to factor, you'd also want to get 0 on one side. I guess it's not like everything else, because you wouldn't do that with completing the square, but like some of the other things that we've done. Then you would do the substitution. So you end up with something that looks like this, which is much more accessible. And then if it's factorable, you would just do it. Right, so you solve the equation, whatever you have to do. I will say this, 7.3, they tend to factor, by which I mean they do. If the problems that you had in 7.3, like when you substituted in, if you got polynomials that didn't factor, what you would end up with when you back substituted would look kind of rough. Like, it's doable, but it's to the point where the simplification at the end would be so long that it would kind of detract from what the problem is supposed to be about, which is really, to solve it by substituting. So I can understand why the author of our book set it up this way, right? I mean, you don't want the simplification to be the focus, right? You want the new concept to be the focus. But that's also a thing where I guess in a way you can kind of take advantage of it a little, right? If you go in like expecting everything to factor, then I think you probably end up doing it a little bit faster that way. But it is true. With 7.3, they do tend to factor. The biggest thing here, believe it or not, and I'm going to change colors because this is so important, and you're not going to believe me at first, because this is always there, right? It's always there at the end, check your solutions. Usually, that's just to make sure that you didn't make any algebra errors or anything. But here, there's a possibility of extraneous solutions, and we really do have to check them. So extraneous solutions are answers that you'll get where if you solve the equation and you get whatever you get probably going to get multiple answers with these. Maybe like with number 3, you're going to get 4. I already know that. There are going to be other ones where you get 2. There will be one at the end where you get 6. That'll be kind of epic when we get to it. But basically, the idea is you can end up with things that look like answers that when you go back and do the check, they don't work. So that's why you have to do it. And that's what an extraneous solution is. It's one that looks like it's a solution, but when you go back and check it, it doesn't actually work. So we're going to see that, although I think we're going to be good to go in this first one because this first one's pretty conventional. And also with this first one, we kind of already know what to do because this is so similar to number 1 with the x to the 4th and the x squared in there. So if we let u equal x squared, then I guess the first thing is we're going to sub. All right, so sub from there to whatever we're going to write here. which I guess would then be u squared minus 4u minus 21 equals 0. And then this factors, right? I mean, you would need a pair of factors of negative 21 that add up to negative 4, so that's negative 7 and 3. So you'd have u minus 7 times u plus 3 equals 0. So, all right, well then that means that u minus 7 equals 0, or u plus 3 equals 0. And if we solve those, then here we'll get u equals 7. Here we'll get u equals negative 3. And then we got a back sub, right? So I guess that would be the next line. So from here to the next line, you got a back sub. And if we go ahead and do that, then what we're going to end up with, since u is x squared, we'll have that x squared equals 7, or x squared equals negative 3. Okay, well then if we use the square root property, since these are set up for it, right? You've got an x squared on one side and just some number on the other. So if x squared equals 7, then x is plus or minus radical 7. And then if x squared is negative 3, then x is plus or minus the square root of negative 3. But then we want to rewrite this so it has an I in it. So we can rewrite this as plus or minus the square root of 3 times the square root of negative 1. That's supposed to be a 1. I guess that looks better. So then we can say, well, this will be plus or minus the square root of 3 times I. Okay, so there are 4 possible answers, right? I'm saying possible because we're saying, you know, well, there could be an extraneous solution. We're going to find out. So radical 7, negative radical 7, radical 3i, negative radical 3i, and then we just have to go through and check them all. Okay, so different color perhaps for the check. All right, so let's see what kind of room are we working with here. Let's see, I think I can get radical 7, negative radical 7 up here, and then the imaginary ones underneath. We're going to find out one way or another. With this problem, the check is actually far longer than the actual problem because there are 4 numbers that you have to check. And so that means this actually kind of takes a while. But one thing that will happen is that like when you have like the plus or minus ones, usually like those end up being so similar in the check that the second one's really fast. I mean, there is that. But the first one, x equals radical 7, if we're going to do that check. So what I like to do here is just sub in on the left side and see if I get a 0. So like rather than like setting the 2 sides equal to each other or anything like that. So let's just see what happens if I sub in. So I'll have the square root of 7 to the 4th minus 4 times the square root of 7 squared minus 21. And if you don't really see what's going to happen with these, you could rewrite a square root as raising to the power of 1/2. So I'm going to do that just in case that makes this look a little more explicit. I guess that's the word that I'm looking for here. So every radical 7, I'm just going to write a 7 to the 1/2. So that's where we are. But then we have that rule about when you raise a power to a power, you can multiply them together. So this 7 to the 1/2, which is then raised to the 4th, that's 7 squared, right? Since 1/2 times 4 is 2. And then minus 4 times 7, because 1/2 times 2 is 1, so that's just 7 to the 1st. And then minus 21. So we're going to get 49 minus 28 minus 21. And yeah, that works. Right? This is going to be 49 minus 49, so we're all set. Okay, good. That one's an actual solution. All right, what about negative radical 7? Well, if we do the same thing and we sub in, so let's see, we'll have negative radical 7 to the 4th minus 4 times negative radical 7 squared minus 21. And what you could do here is like this negative radical 7 that's being raised to the 4th. So that thing that's in parentheses, you could view that as a product. Like you could view that as negative 1 times radical 7. And that might actually make this a little bit easier to see. So I'm going to rewrite it that way. It's negative 1 to the 4th times radical 7 to the 4th. Then I'm going to do the same thing with the other negative radical 7. So negative or minus 4 times negative 1 squared times radical 7 squared minus 21. So negative 1 to the fourth and negative 1 squared, those are both 1, right? So what we're going to end up with is 1 times 7 squared. Right? We already know that this is a 7 squared because it happened in the first check, right? So we might as well just recycle that work. And then minus 4 times 1 times 7, again, recycling from the last check. And then minus 21. So let's see what happens here. What we're going to end up with is, let's see, this is going to be 49, and then minus 28, and then minus 21. That looks pretty familiar. And we get 0 like we're supposed to. All right, great. What about the other ones? So radical 3i and then negative radical 3i. Well, let's see. So if x is radical 3 times I, like that. So let's see. If we sub in square root of 3 times I to the fourth minus 4 times square root of 3 times I squared minus 21. And we can do what we did in the last one, where if you view what's inside the parentheses as a product, so like the radical 3 times I all being raised to the fourth, you could say, well, then that's radical 3 to the fourth times I to the fourth. And that's what I would do with this thing. So I'm going to rewrite this as radical 3 to the fourth times I to the fourth minus 4 times radical 3 squared times I squared minus 21. And then, since by definition I is the square root of negative 1, then when you square I, you would have to get negative 1, right? So then I squared is negative 1, but then I to the fourth is I squared squared, so that's 1. All right, so let's see what we're actually going to get out of this. We're going to have, and I'll rewrite this as the 3 to the 1/2, again, like we did with the last one. So that'll be to the fourth, and then times 1 minus 4 times 3 to the 1/2 squared times negative 1, and then minus 21, like that. So then the 3 to the 1/2 then to the fourth, that's going to be 3 squared, and that's multiplied by 1, which really isn't going to do anything. But I guess I can leave it in there for now. And then minus 4 times 3 times negative 1, and then minus 21. So let's see, then that's going to be 9 for that first term minus negative 12. Since 4 times 3 times negative 1 will be negative 12. And then minus 21. So that's 9 plus 12 minus 21, which is certainly 0. So yeah, we're going to go with that one. And then the last one, so for x equals the negation of the square root of 3 times I. All right, so let's see what happens here. So negative square root of 3 times I to the fourth minus 4 times the negation of the square root of 3 times I squared minus 21. I guess inside the parentheses, you could view that as a product of 3 things, like a negative 1 times a radical 3 times an I, and that's what I'm going to do with this. So negative 1 to the fourth times radical 3 to the fourth times, having the I in parentheses looks weird. I don't think I'm going to do that. Too weird looking. I to the fourth. There we go. Minus 4 times negative 1 squared times square root of 3 squared times I squared, and then minus 21. All right. Negative 1 to the fourth, negative 1 squared are both going to be 1. So you can kind of see what happens. We're going to get the same thing we did in the last one. We're going to have 1 times 3 squared times 1 minus 4 times 1 times 3 times negative 1 for the I squared, and then minus 21. So this first product is going to be a 9 minus negative 12 minus 21. So that's 21 minus 21, which is 0. So they all work. All right, that was a lot of effort to show that they all worked. But yeah, these are good to go. They're part of the solution, and so are these. So all 4 of them worked. That's not always the case, but it was here. And for future examples, I probably won't do the entire check like this, where it's all 4 of them, because if I do that for every single one, this video is going to be 3 hours long. And we're going to try to avoid that possibility. All right, so the next one, another one where it's kind of similar to something on page 1, where you go, oh, I see what u should be. It should be n plus 4, right? That's the thing that's being squared. Then it shows up again in the second term. So yes, it should be n plus 4, although the first thing, and I guess you could substitute in first if you wanted to, but I would prefer just to get a 0 on the right side first. So I'm going to subtract 14 from both sides in order to get that. So we're going to have n plus 4 quantity squared plus 5 times n plus 4 minus 14 equals 0. And then, yeah, we're going to let u equal n plus 4, and we're going to sub it, right? So that's the next step, is we are going to sub right here. All right, and then if we do that, then we're going to end up with u squared plus 5u minus 14 equals 0. And that's factorable. Right, a pair of factors of negative 14 that add up to 5 are going to be 7 and negative 2. So u plus 7, u minus 2 equals 0. So u plus 7 equals 0, which would lead to u equals negative 7. And then u minus 2 equals 0, which would lead to u being equal to 2. Then we got a back sub because we want our answer to be in terms of n, the original variable, not in terms of u. So, okay, we'll do that right here. So back sub. All right, so then we can just put an n plus 4 in for u. So n plus 4 equals negative 7. N plus 4 equals 2. So then you subtract 4 from both sides, I guess, in each one of those. Here you're going to get negative 11, and then here you're going to get negative 2. All right. The checks on these are fast. So I said I wasn't going to do the full check, but I lied. I'll do the full check on this one because it's actually really short. So the check. So n equals negative 11. If we sub in, so I'm just going to sub in on the left side of this and see if I get a 14. So let's see what happens. So we have negative 11 plus 4 quantity squared plus 5 times negative 11 plus 4. And that's going to be, let's see, negative 7 squared plus 5 times negative 7. And so that's 49 minus 35, or 49 plus a negative 35, whichever. And you get 14. And that's what you want, because that was what was on the right side in the original equation. So negative 11 works. And then what about negative 2? Well, let's see. We'll get negative 2 plus 4 quantity squared plus 5 times negative 2 plus 4. And so that's going to be 2 squared plus 5 times 2. And that's 4 plus 10. So that is also 14. That one also works. So both of these are going to be part of the solution. All right. Number 5. All right, number 5. If you look at it, you go, okay, that looks weird. It's got a square root in the original equation. We haven't had that happen before. No, we haven't, but number 5 is kind of like number 3. Because number 3, if I go back up to it for a second, it had an x to the 4th and an x squared. So you have one of the powers being twice the other power, right, of the powers of x that show up. And then if you go to number 5, that's still happening because the square root of x is x to the 1/2. Right? So what you could do here is you could say, well, this is the same thing as saying x plus 3x to the 1/2 minus 54 equals 0. And x to the 1st being that first term, you go, okay, yeah, 1 is equal to 2 times 1/2, right? So it's still kind of in that format. It looks different because it's got a radical, but it's still, you got one power that's twice the other. And I guess maybe to make this slightly more explicit, you could write that x as x to the 1/2 squared, which seems like an overly complicated way of writing x, but I'm trying to write it so there's an x to the 1/2 in it, plus 3x to the 1/2 minus 54 equals 0. And now you can see, right, okay, yeah, x to the 1/2, that's the thing that you want to sub for. All right, let's do it. So we're going to let u equal, I guess, either x to the 1/2 or radical x if you don't do the conversion to writing it with an exponent. If you still write it with a radical, that's totally fine. Either way, you're going to end up with u squared plus 3u minus 54 equals 0. So then that right there, that's the sub. All right, so then we should be able to factor that. And if you look at that thing on the left, you go, we need a pair of factors in negative 54 that add up to 3. That's negative 9 and positive 6, so u minus 9. Or I'm doing this the other way around. It's u plus 9 times u minus 6 to get a plus 3 in the middle. For some reason, I was thinking it was a minus. It's not. All right, so then that'll work out. And so then if u plus 9 equals 0, and then u minus 6 equals 0 with the zero product property. So either u equals negative 9 or u equals 6, right? And then we're going to back substitute because we want the answer in terms of x, not in terms of u. So back sub. All right, so if we go ahead and do that, then what we're going to end up with is that radical x equals negative 9 or radical x equals 6. But we don't want this solved for radical x. We want this solved for x. So you think, well, if we square the square root, that should give us an x back out, right? All right, yeah, that's a lot. It seems pretty logical. So if we do that, we'll get the square root of x squared equals negative 9 squared. And then over here, we'll have the square root of x squared equals 6 squared. So in the first one, we're going to get that x is 81. In the second one, we're going to get that x is 36, right? Just from squaring 6 and then squaring negative 9. Okay. And then we're going to check them, just like we've been doing. And I think I can put a little barrier over here. All right, so for the check, so for the first one, which is that x is 81. All right, if I sub in, I'm going to have 81 plus 3 times the square root of 81 minus 54. But the convention is when you have a square root like that, you would take the positive square root. So this is going to end up being 81 plus 3 times 9 minus 54. And if you're looking at this and going, that's too big, there's no way this is going to be 0, I would absolutely agree with you. It is not going to be 0. It is going to be that, which is 108 minus 54, which I guess itself is 54. So 54, which is not 0. So what does that mean? If we couldn't get what was on the right side of the equation, that means that x equals 81 is an extraneous solution. So an extraneous solution. So this is the thing you have to be careful about, right? Like, they happen. And that's why we did the check, so we could catch it. So this one, no. Right? That's extraneous. That's what that big X means. Stands for extraneous. And then if we check the other one, so the other one being 36. All right, so let's check the 36 and see if this one actually works. So if 36 plus 3 times the square root of 36 minus 54, and that'll be 36 plus 3 times 6 minus 54. But 3 times 6 is 18, so that's 36 plus 18 minus 54. That works. That's 54 minus 54, so you get 0. So this one works. So the solution here really is just 36. The solution is just x equals 36. Or if you want it in set notation, it would be the set consisting of only 36. Okay, so first of all, why does the 81 mess up? Because it's not really like a magical thing. The reason that the 81 messes up, it's actually back here. And I need a different color maybe to point at this. Like a lime green, I think that's what I'm working with here. It's that step right there. It's where you have the square root equal to the negative. That's the thing that causes the problem. Because in order to solve for x, we squared both sides, right? So you get the 81, but then by convention, when you have just the square root of 81 that you have to simplify as part of this expression when you're checking, then you would take the positive square root. So you have a 9 instead of a negative 9. And that's what messes it up. So when you have a square root equal to a negative, that's what's going to give you the mess. That's what's going to give you the extraneous solution. And it doesn't have to work like this, where if there's a square root, it's going to be that one of your solutions works out and the other one's extraneous. It doesn't have to go like that. It could be that they both work, and it could be that neither of them work. And that's actually the reason that I put number 6 in here, just to kind of make that point. So number 6 looks like number 5 because it's got the x and the radical x, right? So pretty clearly we can see what we're going to do, right? We're going to let u equal radical x. So then if we sub in, we're going to get 5u squared plus 16u plus 3 equals 0, right? So I guess there's my sub. And then that does factor. So that would be the next step, would be to do that. And we would have 5u and u to get the 5u squared, right? That's the only option. And then in order to get that 3, but with a positive middle term, both of these numbers have to be positive, so it looks like it's got to be a +1 there and a +3 there to get that middle term to be 16, right? If you put them in the wrong order, you're not going to get the 16. You're going to get 8. All right, so anyway, here, if you go through the solving, so you'd have 5u plus 1 equals 0, and then u plus 3 equals 0. If you solve this one, it's 2 steps, but you'd get that u equals -1/5. And then here you get that u is -3. And then if you back sub, we're going to get the problem in both of these, where we have a square root equal to a negative. And so what's actually going to happen here then, if I guess kind of going on what I said a couple minutes ago, is that what's going to happen is it's going to look like we have 2 solutions, right? 'Cause then if I square both sides, here I'm going to get that x is 1/25, and then with this one I'm going to get that x is 9, right? So just squaring both sides in both of those. The number of solutions we're actually going to have is 0. Both of those are going to be extraneous because they got the square root equal to the negative. And if you go through and check them, it'll be the exact same thing that happened with the 81 up above. So if we go through the check here, then the first one was, let's see, 1/25, which seems like it's going to be worse than it is. Like, it seems like it's going to be a little rough because it's a fraction, but it's actually not that bad. So 5 times 1/25 plus 16 times the square root of 1/25 plus 3. The square root of the fraction you can actually rewrite a little if you want to. So the 5 times 1/25, that's just going to end up being a 1/5. So I'm just going to put it in there right now. And then if you have the square root of a fraction, you can write it like this, as the fraction of square roots. So like the square root of 1 over the square root of 25, like that. And then the square root of 1 is 1, square root of 25 is 5, right? So you'd have 1/5 plus 16 times 1/5, and then plus 3. And if you're looking at this and going, I'm not sure exactly what that is, but there's no way it's 0 because it's just a bunch of stuff added together, right? Like, how do you get back down to 0? There's no subtraction in there. That's the right idea, right? Like, this is going to fail because what you're going to end up with is 1/5 for the first term plus 16/5, and then that 3 you could rewrite as 15/5 to get a common denominator, right? Just multiplying by 5 over 5. And you're going to get 32/5, and that's not 0, right? No argument there. So that one's going to fail, right? So big X for extraneous. And then x equals 9, we're going to run into the exact same problem. So when x is equal to 9, you'd have 5 times 9 plus 16 times the square root of 9 plus 3. And so, all right, that's 45 plus 16 times 3 plus 3. And then you go, that's not a 0. It's a bunch of numbers added together. It's some positive number. Right, so 45 plus 48 plus 3. Yeah, that's 96, which is also not equal to 0. So nothing there. All right, so the solution, it's the empty set. Nothing actually works. So the solution here is empty set. Or I guess if you prefer the more literal empty set with the 2 brackets with nothing in them, you can write it that way too. So I stuck number 6 in here just to point this out. It doesn't always have to be like one solution works, other one doesn't. It could be that they both work. It could be that neither of them work. And actually, to go from this one where neither work to get one where both work, if it was a minus 16 radical x instead of a plus 16 radical x, you'd get 2 solutions that actually worked. So that is a possibility. All right, but then number 7, well, number 7 has cube roots. Okay, we've had cubes before. They look a little bit different right now because of how they're written as fractions, but you can see what's going on here where you've got one of those exponents being twice the other, right? 2/3 is 2 times 1/3. So it looks like what we would do with this, I'm going to rewrite this slightly with the power raised to another power idea again, because you could write that y to the 2/3 as y to the 1/3 squared. Like that. And so then you'd say, okay, well then u must be y to the 1/3. And that's true. That's what we're going to do. We're going to let u be that. So then you'd have 3u squared minus 2u minus 1 equals 0. So then what we've got here is the sub step. And then we're going to have to factor that. So 3u and u to get the 3u squared. And then to get the minus 2 in the middle, it looks like we need a minus 1 there and a plus 1 there. All right, so then we'd have 3u plus 1 equals 0, and we'd have u minus 1 equals 0. So then here you get that u is negative 1/3. Here you get that u is 1, and then we're going to back sub. Right, so if we do that, you'd have y to the 1/3 equals negative 1/3. And here you'd have that y to the 1/3 equals 1. Okay, well, when we had square roots and we wanted, if we had the square root of x equals some number and we really wanted that solved for x, then we would just square both sides. Here, when we have cube roots, we got to cube both sides. All right, makes sense. Right, so if I cube both sides here, so y to the 1/3 cubed equals negative 1/3 cubed. And then over here, y to the 1/3 cubed equals 1 cubed. So the one on the right's easier, right? That's just going to be that y equals 1. And then the one on the left is going to be that y is equal to negative 1/27. So there, right, negative 1/3 times another negative 1/3 would be 1/9, and then times another negative 1/3 is negative 1/27. And then if we check these, so let's see. I guess we've been doing black for the check. Keep that going. All right, so for the check, First one would be, I guess, just going left to right would be the negative 1/27th, because that's the one that looks like it's going to be trouble. I mean, for the 1, I would argue you can just look at it and you know that's going to work. Because the cube root of 1 is 1. So just, if you look at it, you go, yeah, you're going to get 3 minus 2 minus 1. That's a 0. Fine, right? The negative 1/27th, I think, is worth going through, though. All right, so negative 1/27th. Let's see what we get out of this. So we'd have 3... Uh-oh, I lost my ability to write. 3 times negative 1/27th to the 2/3 minus 2 times negative 1/27th to the 1/3, and then minus 1, and we'll just have to see what we get out of this. The way to handle this, like raising to the 2/3, would be to do the denominator first. So, like, basically then you would have the cube root, or yeah, 3 times the cube root of negative 1/27th, which would then have to be squared, minus 2 times the cube root of negative 1/27 minus 1. The cube root of negative 1/27 is negative 1/3, right? So you get 3 times negative 1/3 squared minus 2 times negative 1/3, and then minus 1. That's going to be 3 times 1/9 minus, well, I guess minus negative 2/3 minus 1. So it's going to be 1/3, right? Because that'll be 3/9, so it's 1/3. Plus 2/3 minus 1. Yep, you get 0. That works. So both of these work. We don't run into the problem that we had before. Specifically, we didn't get it when we had the cube root equal to a negative. So with cube roots, this isn't a problem. And one way you can think about it is that, like with cubes, there's only one number that you can cube and end up with any specific number. What I mean by that is, like, what do you cube to get 8? 2. That's it. Right? If you cube negative 2, you get negative 8. So there's a one-to-one correspondence. That's the idea with cubes, where if you cube some number, you get some other number, but that's the only number that you could cube to get that number. Right? As opposed to squares, right? There are 2 different things that you could square to get 16. You could square 4 or you could square negative 4. Right? And you can pick any positive number and make that argument. Right? There are 2 things you could square to get 100. Right? Plus or minus 10. There are 2 things you could square to get 17. Plus or minus radical 17. So you can always do that, and that's what causes the trouble when we have square roots. So really what it comes down to is where you really have to check and make sure that you don't have any extraneous solutions. Really, it's for when you have even roots. So like other even roots, like 4th roots, they would cause the same kind of problem, but they don't show up in this section. So generally that's true, that it would be even roots. But for this section, the only even roots that show up are square roots, so just focus on them. If you see a square root, that has to be like a red flag, like whatever I get as my answer, I better check it because it might not actually work. Everything else you would actually be fine. So like if you're pressed for time, just make sure you check the ones with square roots in them. The other ones, you're basically checking to make sure your algebra is right. But with the square roots, that's where you might have an extraneous solution, and that's where you got to be careful. And you have to make sure you do the check and check every possibility. And I guess if you're, kind of astute to what the pattern is here, it's anything where the square root is equal to a negative that's going to cause a problem. You could also do it that way. So if you want to jump the gun a little bit, and like if you see square root of x equals -5, and you just go, nope, that's going to be extraneous, and just throw it out, you will be right. It's probably better to check it, but that's one of those things where if you're pressed for time, this is the way that it always works. Whenever the square root of x is equal to a negative, that's when you run into trouble. So it's not really like that's a shortcut because there are no exceptions to it. That's always the way that it works. But cube roots, they turn out okay. All right, let's see. Next, negative exponents. We can have those. There are two ways of handling this, actually. One of them is to use a substitution. Because you could say, well, that a to the negative 2, that's a to the negative 1 squared, right? Because negative 1 times 2 would be negative 2. So you could do it like that and say that that's 10 times a to the negative 1 squared minus 11a to the negative 1 plus 1 equals 0. And then here you're going to let u equal a to the negative 1. So then you'd end up with 10u squared minus 11u plus 1 equals 0. And then, because this is section 7.3, that's going to factor. So we can go ahead and do that. And it looks like what we're going to get is 10u minus 1 times u minus 1, right? Because we need, it's either, I mean, I guess you don't really have any options, right? If this is going to factor, you have to have two factors of 1 that give you a negative middle term. That's got to be -1, -1, right? And then I guess you're just picking the 10u and the u instead of the 5u and a 2u. But 10u and a u does give you that -11 in the middle. So then you'd have 10u minus 1 equals 0, u minus 1 equals 0. So then this will end up eventually being that u is 1/10. This one is that u equals 1. And then we have to back sub. So then a to the negative 1 is 1/10. And then here a to the negative 1 is 1. All right. So if we back sub, we end up there. All right. So then we want this to be a equals, not a to the negative 1 equals. I think the easiest way to see what to do is to rewrite that with a positive exponent. So a to the negative 1 is the same thing as 1 over a. So 1 over a is 1/10, or 1 over a is 1. And then if you took the reciprocal of both sides, which maybe you don't even have to, right? Just looking at this, you go, well, 1 over a equals 1 over 10. It looks like a has to be 10. Yeah, that's the way that goes. So yeah, a would be 10 there, and then here a would have to be 1. Which you could get from doing the reciprocal, or in this case, I think just kind of looking at it, you could go, yeah, I mean, if a is not 1, I don't know how you get a 1 on the right side and get that equation to hold up. So those are the answers. And they both work, which you can go through and check them if you want to, but I actually don't have the space because I have to do something else. The something else that I have to do is, and that's why I actually wrote this, the let u equal a to the negative 1, so close to where I was writing the other stuff, because I needed all this space over here. The other thing that you can do, and I'm going to start over at the beginning just to point this out, because what I did on the left side is not naturally how I would solve this. It's not wrong, it's perfectly correct, but it's not the first thing that would jump into my head. The first thing that would jump into my head is what happens if you rewrite that with positive exponents. So I would say, well, then this is going to be 10 over a squared minus 11 over a plus 1 equals 0. But then you could clear those rational expressions, where if you multiplied both sides by a squared, so a squared times this whole left side, and then, let's see, I guess distributing it wouldn't hurt. So a squared times 10 over a squared minus a squared times 11 over a, and then plus a squared equals 0. All right, this first term, those a squareds are going to cancel, and that's just going to be a 10. Then here, the a in the bottom is going to cancel with one of those, so this will be minus 11a plus a squared equals 0. I'm going to rewrite the left side in standard form as a squared minus 11a plus 10 equals 0. And then to factor that, we need a pair of factors of 10 that add up to negative 11, which would be negative 10 and negative 1, right? So you'd have a minus 10 equals 0, and you have a minus 1 equals 0, so you get that a equals 10 and a equals 1. And so you get the exact same answers. It doesn't really matter which way you do this. I know this is the section about solving by substitution, so you would think the one that's in blue is the one that you're kind of supposed to do. I mean, maybe, but that's only really in the context of because it's showing up in this section. Right? The blue one on the left and the brown one on the right, they both always work if you have this kind of setup where you have those negative exponents like that. My natural reaction is to do the brown one. Like that's just the one that I see first. And you may not. You may see that as, oh, -2 is -1 times 2. I should do substitution. Fine. You're going to end up with the same answer. Whichever one you see right away is probably going to be the one that's going to feel easier. Right? Because easy is subjective. Right? So usually that's the way it is. Right? The one that feels like it's working with your intuition, that's the one that probably feels easier. And so that's what I would do. Right? They're both going to work. Number 9 is actually the exact same concept. But I think number 9 is telegraphed a little more to where I would wager that a higher proportion of people would do number 9 just by clearing those expressions, just from the way that it's written. That's what I would do with that, although you don't have to, right? You could do it the other way, but I think I would do that by... And I'm just going to say MBSB for multiply both sides by, but multiply both sides by x plus 1 quantity squared. That's what I would do with this. And so then you'd end up with x plus 1 quantity squared times 2 over x plus 1 quantity squared plus x plus 1 quantity squared times 5 over x plus 1. And that would be equal to x plus 1 quantity squared times 3. And then, let's see, you could cancel those. Then here, the x plus 1 down there, you cancel one of those. So you'll have 2 for the first product plus 5 times x plus 1. And then that's going to be equal to 3 times x plus 1 quantity squared. Let's see, I guess we can distribute that 5 on the left, so it'll be 2 plus 5x plus 5. And then on the right, we'll have 3 times, if you square that binomial, x squared plus 2x plus 1. And then, let's see, I guess combining stuff on the left, we get 5x plus 7. Distributing the 3 on the right, we get 3x squared plus 6x plus 3. And then I would just go ahead and get a 0 on one side, so minus 5x minus 7, and minus 5x minus 7. So 0 on the left, and on the right we get 3x squared plus x minus 4. So I put the 0 on the left this time. You don't have to, right? I mean, you can rearrange it so it's on the right, but there's no rule that it always has to be on the right. It can be on the left, and then you just factor the thing that's on the right side instead. So I figured maybe that was worth it this time. We're going to need, since this does factor again, so a pair of factors of -4 that'll give us that plus 1 in the middle. Let's see, plus 4 minus 1 like that, right? Minus 3x plus 4x, that'll do it. And so then from there, you'd have that 3x plus 4 equals 0, or x minus, oops. I was about to just write that as x equals 1, which is true. X does equal 1, but I'm kind of one step ahead of myself. So x minus 1 equals 0. Yeah, x equals 1, and then here x is -4/3. And those are going to be the two answers. The other way that you could do it, and I'm not going to do this all the way out, but I do want to point this out. You could do number 9 like this, as like 2 times x plus 1 raised to the power of -2 plus 5 times x plus 1 raised to the power of -1 equals 3. And then you could do a u substitution, right? You get a 0 on the right, you do a u substitution, and that will work. I think that one's significantly longer here if you do it that way, but it's not wrong. You'll eventually get the same exact answers. You'll end up with a 1 -4/3. So that's another option. All right, then the epic finale here. And it looks innocent enough, right? You know, well, it's like number 3, where we had an x to the 4th and an x squared. It's just now the powers are a little bit bigger. Yeah, they're that. But this is actually going to be kind of involved. You'll see. You'll definitely see. We need to. I wouldn't say we have to empty like the bag of quadratic equation tools, but we got to pull a lot of the tools out for this one. So let's see what happens. I would get a 0 on one side first. And actually, just kind of looking at this, there are going to be 6 answers. Right? We've got an x to the 6th in it. There will be 6 answers. Just like when we had an x to the 4th, there were 4 answers. One of them you can probably see immediately, which is -1. Right? Because then if you have a -1, -1 to the 6th is 1, -1 to the 3rd is -1, so you end up with 1 plus 26, which is 27. So -1 is one of the answers, but the other 5 we're going to have to work for. So I guess then subtracting 27 from both sides, you get x to the 6th minus 26x cubed minus 27 equals 0. And I guess to make it more apparent what's getting squared, x to the 6th you could rewrite as x cubed squared. Then minus 26x cubed minus 27 equals 0. And so then what we're going to do is we're going to let u equal x cubed. Right? So that seems pretty logical so far. And then we're going to sub in. So what we're going to end up with after we sub in is going to be u squared minus 26u minus 27 equals 0. And then we're going to need a pair of factors of -27 that add up to -26. That's not so bad. -27 and 1. Right? So you say, okay, well, that's u squared. Or u squared. That's u minus 27. So u minus 27 times u plus 1 equals 0, right? But then we got to back substitute because we want the answer in terms of x, not u. So back substitute. And then what we're going to end up with is, let's see, x cubed minus 27 times x cubed plus 1 equals 0. So if you use the zero product property, you get x cubed minus 27 equals 0, or x cubed plus 1 equals 0. And notice what we got. The one on the left is a difference of cubes, and the one on the right is a sum of cubes, right? Because the one on the left you could write as x cubed minus 3 cubed, and the one on the right is x cubed plus 1 cubed. And so we do have a way of factoring those, which is also in section 4.5. All sorts of callbacks to section 4.5 here. But if we were going to factor this thing, it would be x minus 3, right? Because the sign of the binomial matches the sign of the original sum or difference of cubes. And that would be multiplied by x squared plus 3x plus 3 squared, which would be 9. And then that'll be equal to 0. And then over here with the sum, you could write that one as x plus 1, right? Because then in the binomial, we got to have a plus because we had a plus here with the sum of cubes, times x squared plus, I guess, 1x, and then plus 1 squared. All right, so then if we use the zero product property here, then we'd have x minus 3 equals 0, so x equals 3. There's one answer. And then the other one, which we're going to have to handle in a second, will be if x squared plus 3x plus 9 equals 0. Let's see here. If x plus 1 equals 0, then x is -1. And then there, we got to see what happens if x squared plus x plus 1 equals 0. Okay. the x squared plus 3x plus 9 and the x squared plus x plus 1, neither of those factor. So what I'm going to do, because the coefficient of the x is odd, and since that would mean if you completed the square, you would end up with a bunch of fractions, I'm going to use the quadratic formula. So that's what I'm going to do with this. And I'm going to say that then x would be, so I guess generally, negative b plus or minus square root of b squared minus 4ac all over 2a. And if we sub in, we're going to get negative 3 plus or minus the square root of 3 squared minus 4 times 1 times 9 all over 2 times 1. So then it's negative 3 plus or minus the square root of 9 minus 36 all over 2. All right, that's going to be a negative 27 underneath the radical, so negative 3 plus or minus the square root of negative 27 over 2. We could factor out the negative 1, so then that way we would have the I. So negative 3 plus or minus radical 27I over 2. But 27 is actually divisible by a perfect square, which is 9. So you could write this as square root of 9 times square root of 3 times I over 2. And that square root of 9 would be 3. So do I have enough space to get this in? I'm going to gamble and hope that I do. Negative 3 plus or minus 3 radical 3I all over 2. Barely got that in. All right. Okay, so now we're up to 4 answers, right? Because we had 2 up there, and then we got the 2 more because of the plus or minus. Now we got to get the last 2. All right, I would quadratic formula this one as well. So let's see. If we're going to do that, we'll have negative b plus or minus square root of b squared minus 4ac all over 2a. All right, so then a, b, and c are all 1, right? So lots of 1s in this. Negative 1 plus or minus the square root of 1 squared minus 4 times 1 times 1. And then that's all over 2 times 1. So that's going to be negative 1 plus or minus the square root of 1 minus 4 over 2. So that's going to be negative 1 plus or minus the square root of negative 3 over 2. And then we can bring out the square root of negative 1, which would then be an I. So then that's negative 1 plus or minus radical 3 times I over 2. And that should do it. All right. So that's where we're going to end up. And actually, oh, I made a mistake in here. Oh, no. This is actually a minus. Yeah, something didn't look right. That's what it is. So that's a minus. That's actually going to throw a bunch of stuff off. Let's see. That sine, 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 sine. And so then that's a minus right there. Sorry about that. This video is so long that I'm getting fatigued getting my signs wrong. But that does need to be a minus there on that second term of the trinomial, because that needs to be the opposite sign of whatever's in the binomial, right? Just like the one toward the left where it was a minus and then a plus. Here it's a plus, so it's got to be a minus. All right, so yeah, so then basically what happens here is you get the negation of negative 1. I guess I could write it like that. There. Negation of negative 1, which is a 1. So eventually you get 1 plus or minus radical 3 times I over 2. There. Okay, so that covers everything in 7.3. And I know this one was really long, but part of it was because of that big finish with number 10. There's, I think, one like number 10 in the homework. If you can do number 10, you can do the rest of them, right? So even if with number 10, if you're thinking, that looks kind of intense, but I could still follow along with all the steps, that's great. Because then if you could follow along with all the steps to get the 6 solutions there, then the ones where you're only getting like 2 solutions, they're going to feel a lot easier. So, and in a way, that's the point of having number 10 at the end. So in that way, when you go back to the homework and there are the ones that just have a couple of answers, you go, oh, all right, that wasn't so bad. But anyway, that's everything in 7.3. I believe that was pretty long, so it should be everything in 7.3.